Thank you, Julie, and thank you everybody for joining us tonight on our launch for the South East branch. It's an absolute pleasure to be sitting here as your chair this evening. Looking forward to the presentation from Mike, and of course a big thank you to all of you guys that's taken some time out of your evening to join us as well this evening. I'm personally looking forward to this one. So that, like Julie said, that's probably enough rabbiting from me for now. I'm going to hand over to my colleague Katie, who's going to introduce Mike. And again, thank you everybody for joining us on this one. It's an absolute pleasure to see so many of you on this webinar this evening. So thank you again. Katie.
Thank you, Paul. Hello everyone, I'm Katie Jenner. I've recently taken on the role of Events Coordinator for the South East of England branch of IIRSM. It is my privilege to introduce to you as speaker for this branch relaunch webinar, Mr. Mike Frayne. Mike has contributed many years of experience and knowledge to the electrical industry, in particular raising awareness surrounding the management of arc flash risk in a very practical way. Any advice that Mike gives on this subject is as a result of his own extensive experience. Mike is a chartered engineer, a fellow of the Institute of Engineering and Technology, IET, corporate member of the Chartered Management Institute, expert for the British Standards Institute, chair for the International Electrotechnical Commission Arc Flash Working Group, secretary for the IET South Yorkshire Local Group, lead for the IET Arc Flash Working Group, and author of the European Arc Flash Guide, and so much more. Mike's personal mission is to inform and influence duty holders, designers and service providers to reduce danger from electrical arcing by providing quick, simple, accessible and accurate predictive tools coupled with practical advice. We are honoured to have Mike join us this evening to provide an insight into electrical safe systems of work. Mike, I'll hand over to you if I may.
Well, thank you, Kate. That's a lovely introduction. Thank you for that. And it's stolen my thunder a little bit, so I can relax on some of the slides that I've prepared in advance of this. But good afternoon, everybody. My name's Mike Frayne, and it's my pleasure to speak to you about electrical safe systems of work and available means of risk management. Kate's gone through my credentials, I suppose, so I don't need to go too much into that. If I can get my slides to advance, I just want to say a little bit about my work with the IET. The IET, I'm a vice chair of the Engineering Safety Policy Panel, and we've worked on various things since I've been there, one of which I headed up the Arc Flash working group and produced a fact file. In Europe, the amount of information that's out there on managing the arc flash risk is sketchy to say the least. But you know, I'll be speaking about that later. I'm the expert for the British Standards Institute for the TC78 live working group. Also mentioned the IC work that I do as well. I'm expert for the International Electrotechnical Commission for writing standards. I'm a convener for the Arc Flash Working Group number 15, also a project team leader for the IEC Arc Flash Guidance for End Users project team, plus being a member of 5 other project and maintenance teams for that same organisation. And finally, I just wanted to say a little bit about my experience that's not been said previously. I have worked for an abundance of household names. Oh, sorry, I've worked with an abundance of household names across Europe mostly, but and beyond. But I've not worked on an oil platform yet, so I'll put that on my bucket list. I think sooner or later I'll get that pleasure, I'm sure. But worked in senior management position in contracting, utilities, consultancies, and facilities maintenance companies. And why I'm telling you that is that I've had direct responsibility for putting people to work on a full range of complex and large power electrical systems. And as I said earlier, there are very few industries I haven't worked in. I created a company called Electrical Safety UK in 2004, which has gone from strength to strength. And I've been involved in the authorship of electrical safe systems of work since 1990. Nowadays, I've got to say that I'm independent and I can offer an unbiased view of electrical safety, so you can be assured of a practical approach to the subject. So what I'm going to be talking about today, well, it's safe systems of work. It's a very broad piece of work, and the work that we're doing with the IET is to create a new fact file, which is going to be a piece of work that will be out and published, I hope, this year on safe systems of work. It's not just going to be electrical safe systems, it's going to be mechanical and electrical on engineered hazards. And the other thing we're going to talk about is what are the electrical hazards. It's a mixed audience today, so I'll go back, to basics. We are going to be doing risk assessments. We need to know what the hazards are, how we can measure it, and so on, and what the severity of those hazards are, and what are the consequences. So I'll highlight that, and I hope it's not over the top for one or two people that have already, know this stuff. So I know there's a few experts online today, so bear with me. I'm going to have a look at the main causes of electrical accidents. Much of the work, much of the presentation that I'm going to give to you is from my own experience, where I've been asked to investigate what's gone wrong and why, and then from that I want to talk around the subject about how to approach safe systems of work for electrical systems, around the building blocks of electrical safety, and just a sort of a framework that I think is very, very very important to do it in that way. So I'll be talking about the building blocks, and you'll hear all about that later on. And then I'm going to do a section on arc flash risk management and new resources that are available, particularly in Europe, for managing the arc flash hazard. And then finally, I'll wrap up with the electrical safe systems of work and risk reduction strategies. So really prioritising a list of inclusions into a safe systems of work, whether you've got one already or whether you're thinking about writing one, and there's a whole range of people that fit into those categories. So, what is a safe system of work? Well, Hughes and Ferret wrote in the Introduction to Health and Safety at Work, which is the NEBOSH handbook, it's the integration of personnel, articles and substances in a laid out and considered method of working which takes proper account of the risk to employees and others that may be affected, such as visitors and contractors, and provides a formal framework to ensure that all of the steps necessary for safe working have been anticipated and implemented. And in simple terms, what does that mean? Well, it's a safe system of work, and it's defined as in a defined method for doing a job in a safe way. So the hazards then, what are the hazards from electricity? Well, the first one is the passage of current through the body, or electric shock. Next one is blast and heat effects, often called arc flash, arc blast, electrical flashover, and so on. They're the things that create burns, in electrical equipment. And then finally, fire. I know the risk managers out there deal with the third hazard very much, in addition to things that affect personnel So ignition of flammable materials from electrical arcing generally, overloads and so on as well. I'll talk about shock then. I often hear this. I've had electric shocks and it didn't do me any harm. Well, actually, there's three important considerations when thinking about the severity of an electric shock. And the first is the path of the current through the human body. And to have a shock at mains voltage in Europe is usually enough to kill a person. So it's usually the path through the vital organs such as heart and respiratory system that affects whether somebody's going to survive it or not. And you could say that, bearing that in mind, it's the fortuitous path of the current that's missed vital organs. That's why the person is still alive. In other words, the reason that they're still alive is luck. So the next consideration is the duration and frequency of the electrical system. And AC mains, as far as susceptibility to electric shocks for the human body, 50 or 60 hertz is probably as bad as it gets. Lastly, the amount of current is important, and we can see this on the next slide. I'm not going to go through this in loads of detail, but there are lots of factors that determine the amount of current flow, and also the physiological effects on the human body, and gender as well, for instance. So, but the takeaway from this slide is that very little current required to kill a person. As we can see here, an electric shock can have fatal consequences at 30 milliamps or above. And ventricular fibrillation can occur at currents above 100 milliamps. And as we probably know, ventricular fibrillation is a condition in which the ventricles of the heart quiver, causing cardiac arrest. That will require a defibrillator to restart the heart, although in advance of getting that piece of equipment, giving CPR to the victim will keep pumping around the body at about 1 amp, which is the last one necrosis occurs, which is a destruction of tissue and organs through burns and passage of tissue. And then nextly, the consequence of electric shock. Well, clearly what I've explained earlier, death from electrocution, and it happens that this is the biggest killer, electric shock, at work, where people don't survive electric shocks even at fairly low voltages. But there's other things like contact wounds, injury and death from falls, fractures caused by muscle contraction, involuntary muscle contraction, injury to heart, nerves, and reputational damage to the organisation as well. You know, if you're an electrical contractor, it's not good to kill your own electricians. The last thing that I might mention is long-term sequelae, and if you don't know what that is, I'll explain on this next slide. And we've all got used to hearing about long-term COVID, haven't we? You know, that people get COVID and then they're left with long-term circumstances from that. And I believe that there's compelling evidence from what I've read of long-term sequelae, that it is a factor, or in other words, long-term damage that's caused by electrical injury, despite the difficulties in studying the phenomena. The studies mostly in Canada and the USA, where there have been reports of neurological damage, common long-term effects reported that fit into that category, behavioural changes, memory and attention issues, psychological depression, irritability, PTSD, post-traumatic stress disorder, in other words, and physical issues such as generalized pain, fatigue, muscle spasms and headaches. So I've raised that with my own IET Engineering Safety Policy panel, which has members, experts from the UK regulators. So, you know, I'm going to keep an eye on that for future developments, because I do think that there's evidence to show that it is real and it does affect quite a lot of electrical work as it happens. The next one is about blast and heat effects of short circuits, and this is the destructive effects of sustained large power arcing, which is referred to in many different terms, as electrical flashover, as arc blast, arc hazard, and arc flash. Depends where you are, you don't see it referred to as arc flash, by the way, all over the world, but it seems to be the internationally recognised term for blast and heat effects of short circuits. So we'll refer mostly to arc flash as we go on through this presentation. Often arc flash is initiated by electrical personnel working to inadequate safe systems of work. In other words, perhaps they're working live on equipment when they shouldn't be working live. There's no reason for them to work live, and it's a perennial issue in industry. You know, that where safe systems of work need to be written in such a way as to not only discourage live working, but to control it, make sure that it doesn't happen where it doesn't need to happen. Although fatalities are quite rare, you know, in a bad year there might be one, perhaps two, you know, but life in that's within the UK. Sorry, by the way, that's just purely within the UK. Life-changing injuries are quite common with electrical workers. In fact, very common, I think. So, what is it and what causes it? Well, for those that whom this subject is new, let me explain what it is and how it often manifests itself. This low voltage model is one that I've used many times to explain the phenomena to delegates at various seminars and training sessions. Arc flash is usually caused by an inadvertent contact between an energized conductor, such as a bus bar or cable, with another conductor or an earth surface. Put simply, it's insulation breakdown, and very often the insulation in question on low voltage systems is simply air. And sadly, as I mentioned earlier, the cause of insulation breakdown is very often human intervention. In this diagram, you can see two copper bus bars that are separated by a 30mm gap and then connected to a 400 volt electrical source with a respective short circuit capacity of 25,000 amps. It's a sort of output that you get from a 1000 kVA transformer, which is pretty ubiquitous in industry. As you can see, there's no protective device in circuit, only a switch. Connecting the two bus bars is a piece of heavy gauge fuse wire, as you can see in blue there. And when I ask electrical workers the question, what will happen when the switch is closed, they often say that a large amount of current will flow and the fuse wire will simply rupture and blow and rapidly disconnect the circuit. Even electrically biased people, you can be forgiven for thinking that, but actually what happens, and I can tell you what happens is faithfully every time this model is put together, is that the fuse wire will vaporize. It doesn't disconnect the circuit. It vaporizes, and in doing so, it'll ionize the air between the two conductors, and it creates a low impedance path. And large amounts of current will flow immediately, and they'll create temperatures as high as 20,000 degrees centigrade at the arc tips themselves. This will immediately vaporize any element known to man. and there will be a massive expansion of air and vaporized conductor material, which causes an electrical explosion. The thermal effects can be quite horrific in terms of burns. Ultraviolet radiation can cause archi, and the ballistic effects can cause blunt force trauma to anybody close by. The consequences of an arc flash are not just personal injury. Although when we're talking about personal injury where there's fines are concerned, in the UK there doesn't need to be injury. You know, if any arc flash needs to be reported under what we call the UK reporting of disease and dangerous occurrences regulations, or RIDDLE. But that's the same in some other countries as well, by the way. Any dangerous occurrence like that needs to be reported to the authorities. So whilst I don't think it happens very much in practice, you know, it is a consideration. The consequences, quite apart from personal injury, it can range from compensation claims and fines and so on, but also damage brand and reputation. You know, working with a large M&E contractor with a blue chip client base, they'd had an arc flash incident on working out of hours in a supermarket, and it came clear to me that you know, had they been successfully prosecuted, that it could affect their future prosperity and even viability as a result of that, because of damage to their brand. But of course, any accident is damaging as far as reputation is concerned, I would hope anyway. The severe equipment damage that comes with electrical arc flash marks it out from shock, because quite often with shock, somebody you know, is hurt or killed in many cases. You know, there is severe equipment damage, and it's quite often on equipment which is absolutely essential to the particular organisation or production. So not a good idea to blow up the vital piece of equipment that's operating the production, so, which is on the next line there. And also environmental damage. And I might just mention one particular case where I experienced all three. I got called out to a rolling mill in Rotherham near Sheffield, close to where I live, you know, one Sunday afternoon. And when I got there was a substation which had burnt down. It was their main substation, and it was, you know, the result of an electrical capacitor operating at 11,000 volts, which had blown up. It had blown a hole through the outer case and through an oil envelope, a cooling envelope, and sadly the insulation was PCB, or you know, which is a non-biodegradable poison, and all that oil and PCB was about to be discharged in a nearby river, the River Don, and had it done so, they could have been involved in some environmental litigation as a result of that. As it happens, we were able to get hold of a pump to get all that out of a nearby bund before it actually got discharged into the river. So we got by it, you know, without creating the environmental issues that we were concerned about. And I remember a very grateful works engineer there. He said to me, you know, very grateful to you, and we were so lucky that you know, it could have been much worse. Well, I think it was pretty bad in its without the environmental issue. Bear in mind that they'd completely killed the power supplies to the site. And then finally, fire or ignition of flammable materials from electrical arcing. See some statistics up there, and you know, across Europe, there reckons to be, you know, something like 4,000 deaths and 70,000 hospitalizations each year, with figures of you know, in excess of 126 billion, massive losses as a result of fire, which no doubt there are people listening that fully understand, you know, just what the issues are. But I was looking at some statistics online, you know, with the English fire statistics, and also looking at some work that's been done by a German IFS, and they were looking at cause of fires, and it was reckoned that this 32% were caused by electrical faults. Now, bear in mind there's domestics as well in here, but I did a little bit more digging, and actually for non-domestic fires that are not caused by human factors, it's something like 50% of fires in industrial plants and so on are caused of non-domestic fires are electrical causes. Of course, you know, for those people in the know, let's not forget Grenfell that started in a refrigerator. So fire prevention, well, a lot of what I see is in, you know, a lot of what we can do, and particularly in safe systems of work, is think about what the electrical maintenance staff can do, because a lot of fires are started in void ceilings and within unmanned plant rooms. So much redundant equipment and cables that are knocking about, either live or dead, you know, which adds to the problems. Control panel maintenance, I'll show you some slides in a little while on that particular area. And you know, coming further down, lack of fixed wiring and portable appliances tests and inspections, I mean proper inspection and audit regimes for perhaps the ceiling voids and places like that. And finally, arc flash detection devices that are starting to be rolled out even in the UK to the IIRSM 671 wiring regulations in high-risk buildings. AFDDs, arc flash detection devices, are there purely to pick up the low-level arcing that may occur in series arcing, where you've got broken wires, or where there's arcing in equipment at low voltage, of course, and it disconnects those circuits before they, you know, become worse and into fires. So, talk about causes of electrical incidents. Well, within my institution of engineering and technology, there is a fact file that's been there for a little while now, but it's worth reading. It's free of charge, by the way, the IET.com if you want to have a look at it. And it's just purely looking at a list of inspections that were carried out in the southeast of England. So it's quite a large area over a 7-year period. And what the electrical inspector did down there was to look at the sample and find out what the actual causes were. In my view, it's a good sample size. It illustrates the fundamental causes of electrical incidents. And as you can see here in the graph, the investigations by the inspector showed that the overwhelming majority of incidents have a preeminent fundamental cause, which is procedure. In other words, you know, where there is non-compliance with or unsuitability of procedures and systems of work. So if we're looking at the main cause of electrical accidents, you're in the right place today. So that's what we're talking about. Maintenance causes were, you know, 36%, and relate to inadequate there's also a lack of competence. We'll talk a lot about competence today as well. Can adversely affect the performance of both the individual and equipment. And then design goes back to poor, unsuitable standards of design for equipment and systems. So look at about 9% on that. So I'm going to carry on this theme. I hope you'll forgive me for, really looking at the root causes of a lot of issues. In doing so, that, from a risk point of view, you can put the resources in the right boxes, I believe. But what goes wrong is going to be exemplified in the next 8 slides that I'm going to show you, which is my photography, showing actual incidents or accidents waiting to happen. And 4 of the cases appear in chapter 12 of my book, The European Arc Flash Guide, in mistakes, myths and mistakes, chapter 12. So hope that you'll be able to see that at some stage. The first one, something that made me smile one time. Basically, I came to the conclusion that there's a commonality between some maintenance workers and water, and perhaps other things that ingress into control panels. But you can see a control panel there which is wrecked totally. But one guy, I remember him saying to me, if a jumbo jet landed in our car park and our hygiene crew was asked to clean it, it would never fly again. It was in the food industry, actually. That's why they clean the control panel so rigorously. Well, the other quote there is, this lot would manage to get water inside a nuclear submarine. So a bit flippant, but as you can see from the photograph, the damage to this control gear was not just because of water ingress, although there's quite a bit of water in there. It's also caused by road maintenance staff ingress too. So that's a commonality between maintenance workers and water. The next one is, well, it's the same distribution board, basically, or the same type of distribution board. On the left-hand side is a fairly new one. On the right-hand side is an identical one, which is completely destroyed because somebody tried to connect a cable into it while it was still live. It resulted in personal injury, loss of production, HSE investigation, and I was called in on this particular one to provide new safe system of work, including rewriting policy rules and procedures and also training where there wasn't one before. Might be worth saying that the guy who was doing this work that he didn't need to do live was only 19 years of age. So there was another aspect to this story which I could go into, but time is not permitting tonight, I'm afraid. This is another one that I was asked to go and investigate after injury from an electrical flashover. And I was asked to undertake an investigation into an incident which caused injury to a facilities technician being fault finding on a control panel. The picture on the left is a healthy main switch, and on the right is the damage unit which was involved in the flashover. The arc flash was caused by persistent low-level arcing across the contacts whilst on load, so the contacts weren't quite making, and eventually that escalated into a full arc flash. Remember the model I showed you earlier on, where you've got discharge in air. At some stage it becomes a short circuit, and that's what happened here. And if I turn the unit over, you can see that the monoblock is cracked. And what I found is that people, if you look at the center photograph again, you'll see that there's physically three different size fuses in there, and someone in the past, this tried to force a fuse in that wasn't meant for that particular switch fuse, which created the damage. So I would say that's willful damage, and also bear traps that are left for colleagues, because of people that were burned to the result of it. This weren't the people that changed the fuses. Next thing is where there's several examples here of people making things work at any price, whether it's time, I just don't know, but they haven't even bothered to fix the live electrical components back in place again. Quite horrific to see that happening in control panels. Those control panels, perhaps that one on the left, is probably not that old, you know, and you know, if we look again at the next one, again, there's stuff connected in, you know, components that are connected, and they can't be bothered to fix them in place. So more of the same there. But this one, it could be laughable, but it's not really. But someone has removed the insulating shrouding from the main switch here, and it does seem quite comical, but a chemical drum has been cut out and used as improvised shrouding over live connections. Whatever standards we used to design the panels in the preceding slides, as well as this one, the lack of properly written, trained and enforced safe systems of work has allowed this equipment to become unsafe. And as I'd said before, it's become a bear trap for other workers. This is an example where I had to stop a young man who was working inside this panel. It's a refrigeration room, actually. He was undertaking some diagnostic testing using a multimeter above these bare 800 amp bus bars, if you can see in the bottom there. They shouldn't be bare, but that's another question. On further questioning, it transpired that this lad had got very little experience, and the height of his qualifications was a MVQ level 2 in refrigeration. That would take perhaps weeks to achieve in the UK. I eventually found the missing shrouding on the right-hand side picture, and it's slotted on top of a nearby control panel. You know, so somebody's just taken it off, put it up there, and you know, bear in mind that you've got this youngster as well going in there. I don't think that a properly written safe system would ever have allowed that young man anywhere near high power equipment like that. But it tells a tale as well when you've got vital safety equipment being left off a switchboard like that. And I think this is coming to the end of those particular slides, but this is one where I got called out one Saturday. I've got called one Saturday where and there were two guys who ended up hospitalised after initiating an arc flash in a panel that was still live. They had a Saturday morning job actually to clean this panel, and instead of isolating it upstream, they relied on local isolation. The panel isolator, as you can see here, if I just circle it, had the actuator bar and shrouding missing. You can see there's a common thread here, can't you? And the workers thought that the outgoing retrofitted switch used on the right-hand side of the panel was the main isolator. That's that one, which it wasn't. Now, I can go on about this. I could list at least 10 things that went wrong with this incident. Most were to do with inadequate safe systems of work, and we'll speak about the significance. I mentioned Saturday morning. I'll talk about the significance of Saturday morning later. Oh, sorry. I do beg your pardon. I've gone to the end. I pressed the wrong button there, so let's go back. Right, there we go. Sorry about that. We all make mistakes, you know. And we'll see a bit more of that when we talk about human intervention. So this particular model I put together, I created this based upon Guardian Electric, who put together superb duty holder guidance some time ago. And this explains the 3 building blocks of electrical safety. That is, safe people, safe places, and safe procedures. And this gives us a framework, you know, to deal with safe systems of work. So, first of all, safe people on the top there in blue. It deals with competence, information, training and instruction, and of course, supervision and control. Safe places in orange, they're about well-designed and documented installations, maintenance, confidence in protection systems. And what I mean by confidence in protection systems, I mean that the upstream device will operate correctly and safely to disconnect dangerous faults from the electrical system. And finally, safe procedures need to have a risk assessment process with specific rules, with clear responsibilities and authorizations. And it has to be recognised that electrical accidents have causes that involve a number of factors, and that any safe system of work must focus on an integrated prevention strategy and not one that just deals with factors in isolation. So issuing safety rules, for instance, is not going to make the organisation safe overnight. We've got to address the other issues as well. So come to human factors. And here I suppose whenever we introduce people into this management process, and we first have to consider what they sometimes, perhaps they will not behave in the way that we would want them to. We all make mistakes, as you saw my faux pas earlier, and advancing to the end of the slides, but we want to learn from our mistakes, so I'll not press that button again. But sometimes human failure can be deliberate, and this is a serious issue, and it leads to non-compliance, or it can be inadvertent, which leads to errors. Whilst human factors are a huge topic, the following suggestions might help in managing electrical safety risk. So, non-compliance, well, it's a cultural issue generally, non-compliance, I've found. It comes from the top, and it can be an individual refusal to follow rules or procedures, but in either case, it's a problem that must be faced head-on, you know, before the non-compliance becomes an accident. Cultural issues are sometimes very difficult to change in an organisation, and I could speak about that for a while, but it's all about leadership, and it's at management level that we need to start. It's then important that a workforce is involved in any changes to procedures, which involves risk control measures for safe systems of work. And we can also encourage reporting of violations and so on, just make it unacceptable. But I'll talk about the 4 stages of competence. So there's a bit of education that might be required as well in here. You know, a lot of people, well, you might say people don't know what they don't know, and it's about information. You know, can make a step change for electrical safety, I've found. Consultation, getting people on board and involving the workforce in any improvements to safety rules and so on. And also targeted audits, you know, to try and get those things sorted out. Inadvertent errors, well, you know, looking at training, competence assessments, an accompaniment where the high risk tasks where we can't afford errors, and then finally time pressures and tiredness, and it's particularly towards the end of a shift that can be a vulnerable time, I've found. There's a couple of those examples that I gave you, which at time pressure and tiredness would definitely, well, more than two, wasn't there? You know, but they were a factor in some of those practical examples that I gave to you. But a common factor is carrying out high risk activities out of hours that, you know, perhaps that would be normal days off. And I've put there the Saturday factor. I mentioned the Saturday factor because that was where the guys involved in that particular incident didn't normally work on a Saturday. They worked Monday to Friday. Friday night was their night out, and the Saturday afternoon was their beloved football team. So they've got time factors in the afternoon to make sure it's finished so that they could go and watch the football. And you know, although this isn't proven, but I know it is a factor quite often. There's morning after intoxication, you know, from alcohol and drugs on normal days off. So I think the takeaway from that is be aware, you know, that within the risk assessment for putting anybody to work on electrical equipment or anything else, you know, of those factors, those human factors that can cause injury. And there's a specific, I mean, lots of people have seen this before, you know, and gone through this model before, but I've created this this pyramid for electrical safety systems, and we start off at the bottom, stage 4, which is unconscious competence. The people that fall into that category, they're unaware of their own lack of competence and limitations, so they don't know what they don't know. But as you can appreciate, that can lead to a barrier to learning, because they don't know what they don't know what they need to learn, and so on. But going right to the top, we need to have people that are in stage 2 minimum, where the conscious competence, they're fully competent within the bounds of their authorization for electrical work. And something that's worked really well is the next stage of where people are consciously competent. They can do it. I suppose the wrong thing to say is with their eyes shut, but you know what I mean. But they're experts, so they can become advocates for the safe systems of work. And we've introduced engineering safety champions on quite a few jobs that I've been involved with, because peer pressure works really well when we're putting safe systems of work together, where you know, the training and so on is coming from their friends and mates, basically. So a bit about Arc Flash now, and some of the new resources that are out there. And what I've done is I've broken this up into 3 stages, and I'm going to describe what the new resources are about the subject of Arc Flash and risk management. But it's basically, this has been put together for educational purposes at one extreme, right through to a one-stop shop for those who have responsibility to design power systems or put people to work on or near energized equipment, or health and safety specialists and so on. As you can see here, I've ordered the resources into 3 categories. Firstly, the strategy and what you should do, and secondly, the how to do it. And you can see a copy of my book there. And thirdly, the means to carry it out using simple and easily accessible tools and calculators. So this brings us to the first element, which deals with strategy. And if we have a look at that, we've got the IET fact file that I talked about earlier, which is looking very much about strategy for dealing with the fundamentals of risk assessment, when applied to arc flash, and more detail within the European arc flash guide as well. And of course, that particular document, the arc flash risk management fact file, is free of charge again. You can download that for nothing. And this is a very simple model I've just put together from those documents. And it's basically the arc flash risk management model for arc flash. And first of all, we need to, at a basic level, we need to consider 3 actions, and it is another hazard, just like any other, whether it's working at height, wherever it might be. You know, there's variances in severity and so on, but the hazard in this particular case is electrical flashover. And we're firstly asked to identify what could cause injury. In other words, the hazard. So when we look at arc flash, in the first instance, we look at system parameters such as voltage and fault level and electrical protection arrangements. The next one is deciding how likely it is that somebody could be harmed and how seriously, in other words, the risk. And this is derived from system conditions such as the condition of the equipment, the measures, the quality of the installation, measures used to contain and out during switching under normal and fault conditions, how well it's been maintained and whether it's been operated in accordance with its original design. And it's also directly related to the task to be performed, which is an important consideration. And then finally, take action to eliminate the hazard, or if this isn't possible, control the risk. And we'll do this by applying a 4P approach to eliminate or control the risk, which has been put together and published both in the book and also the fact file. So the next part is the how to do it, and that's all within the book. Glad to say that I've had some great feedback, and you know, from across the world, as it happens, people have been very complimentary, and as a result, I'm very happy about that, and really overwhelmed actually. You know, that it seems to have filled the gap, particularly in Europe, where some of the knowledge has been lacking, to be honest. So I'm very happy that the feedback has been given, and it makes all my endeavours worthwhile. So what's the 4Ps all about? Well, this is the model that I put together, and it sort of explains it, which is from the first part. We look at the predict section, and it's there we start, and this is where we predict the level of the hazard, you know, the severity. I'll talk about some of the tools that we would use to do that in a little while. But from that, we'll get results from those calculations, and from those results, we can then examine what prevention strategies we can apply. And we've now gone over into the green segment of prevent. And at that point, we ask ourselves a question: can we apply further prevention techniques? Can we remove it completely? You know, can we minimise it further? And by re-evaluating, we then predict the severity once more, and then create more results. And then once we've exhausted that prevent segment, we can then go into looking at process, which is looking at policies, rules and procedures. And it's back to the diagram I showed you earlier. It's all about safe people, procedures and places. And when all that's done, we then, if there is a residual risk that requires protection by PPE, the purple section here is the one to do it. By that, if we've done this correctly, the PP levels that we are looking at hopefully will have been reduced by applying the prevention techniques that we've talked about, so that any PP that we're creating is going to be less cumbersome, going to be cheaper, and more easily worn by people who have to wear it. So if you have a look in the top right, there is a little wheel showing where we are: predict, prevent, process, and protect. We're actually in the predict section here, and what I'm going to highlight here is arc flash calculations, which is what we use for predicting the level of the hazard. And in this particular case, we're going to look at IIIE 1584 guide for performing arc flash calculations. There are other predictive techniques, but this creates an incident energy level, which would be at the worker themselves. But I do discuss much more than this within the book itself. There's a European box test method where there's an algorithm which is based on that. So there's a slight difference in the way that that's approached. But that's all within the book. But I don't think I've got time to talk about it today. So the IIIE guide, it calculates the arcing current that, for any electrical designer would need the arcing current to think about how quickly it can disconnect the circuits and so on. It also calculates the incident energy, which I talked about. And the incident energy, it defines the severity of the arc flash at a certain distance. It's usually in calories per square centimetre, that the true SI unit is joules per square centimetre. So if we look at a figure of 1.2 calories per square centimetre applied to the skin for 1 second, it's a threshold at which there could be an onset of a 2nd-degree burn. So it's curable, basically. But that figure is often used, not in Europe, it's a slightly different approach, but it's often used for determining the PP requirements and an arc flash boundary. And lastly, the arc flash boundary can be calculated in which the incident energy is reduced by that key number that I mentioned there, 1.2 calories per square centimetre. So the first thing that I talked about, what incident energy calculations do, is give us the calculation for calories per square centimetre, incident energy at the working distance given here, whether it's testing or switching or wherever it is, or reading meters or whatever. And it's a working distance from the arcing source. Next is the arc flash boundary. It gives the information about the arc flash boundary, and this is the distance from a prospective short circuit current where the incident energy is calculated to drop to this magic figure that I talked about before, 1.2 calories per square centimetre, a bit like holding a match on your skin for a second. That's the sort of heat we're talking about. It hurts, but it will recover. It's likely to be a partial thickness burn at worst. So here we're now going into the prevent section. Now, I'm not going to go through all these today, but just the headings. But what we're looking for is looking to manage the risk of harm from arc flash, and this table categorises those risk reduction measures into the first one and most important one, which is dead working. And it must be the principal prevention measure of any safe system of work. that we do things dead on electrically safe condition, as they may say in the States. The next one is ADS, which is automatic disconnection of supply, and this is where it's this detection of dangerous arcing currents and then automatic disconnection of supply through the various means that I've put forward there. The first one on adjusting protection settings is probably the low-hanging fruit of risk reduction strategies when it comes to arc flash. There's equipment design, and there's more and more situations where manufacturers are really getting their act together in providing internal arc suppression and so on, and improved arc protected equipment and so on. And then operational measures, which is all about a holistic approach to system design, installation and maintenance. I'll finish on that slide and then just talk a little bit about one of those issues, and I think it does deserve a little bit of discussion, and that is that testing for dead in order to make safe. It can expose the person undertaking the isolation to the hazard, so it still carries risk. So questions of residual risk and competence of the individual need to be considered at this point. Well, for instance, if safety considerations, perhaps of somebody putting others to work on a high voltage underground cable would be much higher order than somebody isolating a piece of equipment from a local isolator point for themselves. And the first example is going to require somebody with a high degree of knowledge, training, experience. They're going to be working to strict safety rules, applying circuit mainers, padlocks, issuing permits, discharging spiking guns, often under the supervision of a control engineer. And the second example that I gave is an individual isolated for themselves. They can carry a few processes, but risk assessment approach is roughly the same, really. So designers of electrical systems, and this the fourth bullet there, need to consider eliminating live work as part of the overall system design. So installing segregation of power and control, not having them in the same panel, safe control systems, having protection by barriers in place, and built-in test points for testing for that. But the main issue here is that we treat everything as live until it's proven dead. And now we're on to the third P, which is process. And it brings us back to our building blocks of electrical safety. It's the diagram that I put together earlier. And it explains the process policies and procedures from an arc flash, but it's all from other hazards as well. So we'll revisit this towards the end of the presentation. And the fourth P, we're talking about protection. And this again, residual risk. And this is the last line of defence. It's PPs used where the risk can't be controlled by prevention, or where there's a residual risk of injury. And it may be necessary to consider mitigation to prevent injury to a worker by PPE. And I've produced this diagram shown here to show the sort of steps that we should be taking, in the selection of PPE. Again, much more in the book and so on, but it just gives you flavours as to what my thinking is in this particular case. And this has been taken from the European directives on PPE. But firstly, we analyse and assess the risk in the way that I've suggested earlier, through 4Ps. Secondly, define the PPE characteristics, and this, it must be effective against the risks that we've looked at in A, but we also need to take into account other risks, like as well as environmental conditions. You know, it might be a clean room environment or very dirty environment, which might have an effect on the PPE themselves. And then finally, comparing the PPE characteristics in B with availability then. And not everything's available in the market that you might want, although we're getting there with the IEC in terms of providing an IEC standard on hand protection and also head and face and eye protection, hopefully later on this year. And it's at that point we choose PPE, but albeit wherever's out there, you know, it needs to be to a standard and it needs to be tested. And at the moment, those particular areas are being dealt with American standards in the marketplace. So there we go. And then finally, the new resources that I talk about is finished off with online calculator. And I didn't think that providing the knowledge to deal with the strategy and just writing a book would be enough. I thought I teamed up with a very clever computer scientist, Dominic Parr, in order to pull together some simple and accessible tools to give us the means as well as the how here. So this is the last one, which is means. And in here, in the as you can see, you can log on to ea-guide.com. There are a total of 10 tools that are available, including calculators for AC and DC systems, box test algorithm, blast pressure, and also risk assessment forms in the label module in there. And, you know, by registering, you get 7 chapters in my book free of charge, as well as access to videos and instructions by registering. Yeah. Right, well, we're nearly there, and these last 3 slides will just revisit our building blocks of safe systems. And the first one is safe people. And I've put information training and instruction in there, and I think that this is one of the step changes that duty holders can make straight away, you know, where existing systems are lacking, is to make information available very quickly, particularly about the arc flash issues that I talked about. That you know, once people know what the hazard is and how it can hurt them, that's, you know, you're on a step towards dealing with it. Then competence assessments and personnel have a key role in arc flash risk management, as well as electrical safety particularly. Competence assessments require you know, us to look at a framework, a competence matrix I've put in the top right hand side there, which I took from a duty holder that he created for himself, and it's actually sectionalised as a bit of a shopping list for what competence looks like for particular duties on site. So in there, you know, there's appropriate training, professional craft qualifications, there's things like you know, externally assessed cards, you know, safety safety qualifications and so on. Competence assessments themselves is a key issue, you know, for safe people, and contractors need to be dealt with in a similar way, you know, that we have specific authorizations and from that, as I've talked about the competence matrix already, and clearly where we're coming down the hierarchy of risk controls, supervision and control is always got to be of a higher order, where we can't remove the problem at source. Safe procedures. There's requirements for risk assessment in this, and see safety rules there, but and also an IET document for code of practice for electrical safety management as well there. A good starters, but ingredients in safe procedures, needs to be risk assessment, approval of electrical test equipment, PPE tools, all these sort of things need to be controlled and managed, and clear responsibilities and authorizations need to be in the rules. Establishing dead working as a principal requirement, and never just accepting live work as something that we've always done, so we'll always do it. Safe isolation processes need to figure in there, as well as specific control circumstances for where live proximity work has to be carried out. And by the way, there is no difference between live testing and live work of any other sort. There's no such thing as live testing and not being live working. It's the same thing. And then finally, monitoring and review, very important that we learn all throughout, providing the rules and annual reviews and training as well. And then safe places. I'll finish on this. Looking for well-designed installations, well-maintained installations. Quite a lot of what I look at is, is dated. Whilst it's not going to get to that level, well designed and well maintained overnight, it's got to work towards that. And one of the things that I think that we should be really interested in is having this confidence that I talked about in protection systems. Actually, old relays and so on can work quite efficiently if they're tested and proved effectively, and it's having a confidence in protection systems like that that's going to protect downstream equipment from damage, regardless of its age. Organisation of documentation of signal line diagrams and so on available, and making sure that everything is available to people that are carrying out maintenance or whatever. Fires from electrical faults we talked about earlier. Audits of control panels, and there's an example audit form suggesting it's perfect. It's on the right hand side there. That form in itself, from my own experience, would allow people to just have a formal look within their control panels, which is the brains of the operation. If you talk about switch gear and control panels, switch gear and transformers, things like that, generators or whatever, they're the heart of a production facility generally, but the brains is the control panels, the things that control the equipment itself. So these are expensive things to replace if they go wrong, and having audits allows us to find issues before they become incidents, and then carrying out system studies, know what the fault levels are, and perhaps arc flash levels throughout the network as well. I'm going to finish on that point. I'm sorry if I've overrun slightly. I'm just looking at my watch there, and I'll hand back over at this point, and if there are any questions, I'll endeavour to answer them.
You're on mute, Paul.
How about that? Thank you, Mike.
Better.
I found that really, really interesting and quite scary at times in some of those sides as well. So thank you very much for sharing your knowledge and experience with us this evening. It really is appreciated. We've got one question for you from Katie. With everything heading towards battery operated, what are the potential risks regarding DC voltage?
Yeah, there is there is a risk, you know, from fire from the actual cells themselves, which is quite well documented and doing the rounds right now. And also DC arc flashes can be quite powerful, you know. And of course, one thing about storage systems for DC, not always storage systems, by the way, but storage systems for DC, is that you can't switch them off, you know. So they're always live, unless they've been run flat, for instance, that there's no charge left in the cells themselves. But yes, there's a lot being done at the moment to try and recognise the increased risk that these systems are bringing to electrical networks. And I do deal within the book for DC arc flash calculations, so you can carry out calculations on batteries or DC generator outputs or wherever it might be, you know, so that's included as well.
Paul, I've had a few questions come through for Mike. One is, have you come across counterfeit cables using fires? We have come across this issue twice in our workplace in the last 12 months. Interesting.
Yeah, it's a good question, because yes, I have. And it was horrific. It was a large operation in Ireland. I won't tell you where it was, but I did some system studies over there, and I was looking at some low voltage copper cables, and they were insulated with XLPE, polythene, and quite often you can actually see through. You know, the colouring's not quite as opaque as it should be. But in this particular case, I looked at them. I'm sure I can see bare conductors, and you know, clearly what transpired when we were able to do a further investigation and look at quite a few other panels, the same thing was happening, and that was down to counterfeit cable. So I've definitely come across it myself, you know, and I'm quite sure it cost them a lot of money to put that right. They did have to inspect I mean, I think we were able to look at the batch numbers and so on, and do something in that way. But yeah, it is something I've come across, and you've got to be very, very vigilant about any equipment that you buy in, and particularly cables such as that.
Thank you, Mike. We've got two more quick questions, so I'm not sure whether they're quick answers. What does the EU or GB recommend for voltage systems over 15 kV prediction calculations? Do you want me to read that again, or did I make sense of that question?
Yeah. Yeah, I know what you're talking about. I mean, above 15,000 volts, the model I showed you earlier, were, you know, IEEE 1584, it goes up to 15,000 volts, and the answer is it depends, you know, what systems that we're looking at. There's the old Lee calculations, Richard Lee, going back to the 90s, provided calculations for calculating the damage from arc flash for voltages, you know, above 15,000 volts, obviously. There's also if we were looking at overhead lines and things like that, a utility type system where you've got single phase arcing, maybe ArcPro from the US, Canada, and there's also, you know, from the box test calculations in Europe, there's also within DGUV a algorithm which would suggest that it can do voltages higher than 15,000 volts. I'm not quite sure how high it goes that, but it's substantially more than 15,000 volts, but it's purely theory at that point. Whereas the IEEE 1584 calculations are based on about 2,000 tests that were carried out on equipment, you know, so actually in air or in boxes or wherever, and they create curve fitting equations from those calculations, from those arc flash events that were produced in a laboratory, whereas the EDUV system is based upon theory.
Great, thank you. I'll hand back to Paul for the closing.
Thank you, Julie. And again, thank you, Mike, for your time this evening. It's really, really appreciated. And like I said, I found that one very, very interesting. Not coming from an electrical background myself, definitely learned something this evening. So thank you, Mike, for that and your time. Really appreciated. And of course, thank you to all the viewers that have logged in this evening. Again, thank you for your time and joining us on our opening evening, so our launch one for this evening. So thanks again for everyone for joining us, and we do have another webinar coming up on the 28th. That's a lunchtime session at 1 o'clock, and that's going to be presented by a chap called Ian Pemberton from Human Focus, and he's going to be doing a webinar on human organisation performance. So Mike was touching on that slightly, all about human interface and how we as human beings interact with what we do on a day-to-day basis. So that's it, I think, from us, unless there's anything else, Julie, from us.
We've just had one question come in because somebody,
okay.
I'm really sorry, somebody needs an answer to this question. Hopefully it's a quick one. Is anyone aware of any upcoming regulatory requirements to assess arc flash as AE's past responsibility to client, and myself as an AP need some support requesting these?
Yeah. Well, arc flash is a hazard in the workplace. You know, I mean, quite apart from the fact that it damages equipment and so on, that you know, it hurts people. So you know, the starting point within Europe is the framework directive 89391, called the framework directive. It talks about risk assessment and so on, and within there is the principles of prevention and so on, which are then transposed into legislation in the member states, and within my own United Kingdom, Ireland, and so on, very similar. You know, would we have the management of health and safety at work regulations, and it's there basically. There is a requirement. It's not specific that you must carry out arc flash calculations. It's a little bit. It's not prescriptive in the same way that the US and the Canadians do it, where they've got the Canadian CZ standard and the American NFPA 70E, whereas those consensus standards aren't actually mandatory themselves, by the way, but that's a moot point. But within Europe, any hazard which could cause harm needs to be dealt with. And, you know, within the group that I headed up for IET, there are two regulators in there, you know, and we were looking at providing information within the fact file of what you should do to manage the risk from an arc flash incident. So that's probably a good start, and that will probably explain a little bit more than I have, or we've got the time to explain today. But it's just another hazard, you know, and that's basically it. Long, you know, I hope someday that there will be specific information, you know, within the regs. But right now, the electricity at work regs, G85, you know, the electricity at work guidance. Within there, it recognises arc flash as a hazard, and talks about you can't manage to isolate the hazard, that, you know, you've got to look towards PP and so on. So that might be another area that you can have a look at as well. So hope that's helpful. I mean, by all means, drop me a line if you want a little bit more information, and I'll certainly get a few links out to you.
Thank you, Mike. And that's the last question.
Brilliant. I think that's it then, Julie. I think from us, just again, a thank you, Mike, for your time this evening. And again, thank you for everyone that dialed in to watch this webinar. I think that's probably about us. Just to say a quick thank you to our other committee members, obviously Julie for her support, Katie, Alistair and Rob, and obviously myself. And we look forward to seeing you on the 28th for that next webinar on HOP.
Great, and I will be uploading the video to YouTube tomorrow, and you should get an email tomorrow also with your CPD certificate. So I'd like to thank Mike and the rest of the committee, and thank you all for attending, and hope to see you at the next webinar. Good night, everyone.
Good night.
Good night.